Hey everybody, Mr. Cozad here with another video lesson. Today's topic is on solving systems of equations with two variables. If you're one of my students, this lesson comes from section 3.2 in our Algebra 2 textbook. I'm sorry, I lied. It actually comes from 3.1 in our Algebra 2 textbook. I'll do 3.2 later. But this lesson, what our objectives here are is we are going to try to figure out the three methods that we use to solve systems of equations with two variables. Okay, you might want to add yourself a note up here that we're talking about two variables. Okay, three variables, these methods are pretty similar, but we'll do a separate lesson on those later. So the three methods that you're going to learn about today are called substitution, elimination, and graphing. Okay, so if you've never done a video lesson with me before, the best way to do this is to work at your own pace. Feel free to fast forward, feel free to rewind, feel free to go back and watch something again, feel free to watch part of it and come back and finish it later. You can really use this however you see fit, however you learn best. I definitely would advise you to work through these problems with me as I do them. That way you can get not only hear what I'm saying about the problems and see how I do them, but you can practice doing them as well. Okay, so here we go. We're going to jump right into our first problem. Okay, so example 1 says solve the system by graphing. So this one actually defines for us the method that it wants us to use. It wants us to use graphing, okay, and it gives us two equations. Okay, so our first objective here is we want to graph each one of these lines on the same coordinate plane. Okay, so as you look at these two lines, neither of them is in a very useful format. Okay, so what I'm going to have to do here is I'm going to have to, let me make this pen just a little bit bigger. What I'm going to have to do here is I'm going to have to make these, rewrite these in a format that's more conducive for graphing. What I like to do actually with standard form is I like to find the x and y intercept. Okay, so when I let x be 0, okay, I solve for y. So when I let x be 0, I get the y-intercept here to be a negative 11/5, okay? And then I'm also going to find the x-intercept by making y equal to 0. So when I let y equal 0, I end up getting 11/2. So they're my two intercepts. So I'm going to go ahead and graph those 2 points. So the x-intercept is at 11/2, that's 5.5. So I go to 1, 2, 3, 4, 5.5 on my x-axis. Now, a negative 11/5 is a little bit more than negative 2. Okay, negative 1, negative 2, so just a little bit more than negative 2. Now, that's not precise, okay, but we're going to do the best that we can on that. So once I get both points, both intercepts, I'm going to, as carefully as I can, draw a line that connects those points, okay? And I'm going to go ahead and label that equation number 1. And I'll put a number 1 up here as well so we know we're being consistent, okay? All right, so for the second equation, we'll call that number 2. It's also in standard form, so I'm going to go ahead and find the x and y-intercept on these as well. So to find the y-intercept, I plug a 0 in for x, and I end up getting negative 13/4. And then for my x-intercept, when I make y equal to 0, I end up getting positive 13/3. Now again, these are two numbers that are not whole numbers, so they're going to be, I have to be kind of careful about where I graph them. So negative 13/4 is just a little bit beyond negative 3. So I go down to 1, 2, 3, and just a little bit further than negative 3. And then 13/3 is just a little bit beyond 1, 2, 3, 4, just a little bit beyond 4. Okay. So then what I'm going to do is I'm going to connect those two. Oh, switched it. So I'm going to connect those 2 points. Okay, the best I can. And when we solve a system of equation graphically, what we're looking for is we're looking for the point where they intersect. Okay, so this is the point that we're looking for here. Now, sometimes what we want to see is we want to see if we can tell what the coordinates of that point are without using a graphing calculator, okay? So if you're very careful with your graph, it certainly looks like the coordinate of that point there is 3, negative 1. But to be sure, what we can do is we can check the point 3, negative 1. And the way that I check that is I'm going to plug that into each of the two equations. So into equation 1, I'm going to plug a 3 in for x and a negative 1 in for y. So that ends up getting me 6 minus negative 5 equals 11. And 6 minus negative 5 is, in fact, 11. So 11 equals 11. So all that tells me right now is that the point 3, negative 1 is a point on equation 1. So I'm going to go ahead and test that same point on equation 2. So again, plug a 3 in for x and a negative 1 in for y. We end up getting negative 9 minus 4 equals negative 13. And we see that negative 13 does, in fact, equal negative 13. So what we found is that 3, negative 1 works for both equations. So we can say that 3, negative 1 is our solution. Okay, so 3, negative 1 is the only combination of x and y that makes both of these equations true at the same time. So as we solve systems of equations, our answer will always be in the form of an ordered pair because you're looking for an x value and a y value that make both equal at the same time. Okay, so let's go on to our next question. Same direction, solve the system by graphing. You have two equations here as well. What I would suggest doing is I would pause the video now and I would try to graph each one of these on your own to see if you can find the point where these two lines intersect. Okay, welcome back. Hopefully you paused the video and you graphed this and you saw that the intersection point is actually really easy to see on this problem. Okay, so I'm going to rewrite, again, both of these are in standard form, so I'm going to find the x and the y intercept here. Okay. The x and y intercept on equation 1 are both at 6, respectively. So let's go to 0, 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4, 5, 6. So that, again, is equation 1. I'm going to connect those points. Okay. And we'll call that, again, equation 1. And we'll label it up here as well. Switch colors here, and let's call this equation 2. Sorry, that's ugly, 2. Equation 2. So when I rewrite the x and y intercept on equation 2, when I let x be 0, I get y as 6. And when I set y equal to 0, I get negative 10. Okay. Now, negative 10 is hard to show on this particular graph, but that's okay because we see that that y-intercept actually lands right on top of the y-intercept from equation 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm just going to kind of estimate that that point's out here somewhere. It's just enough to see that line. Okay. And very clearly, again, we know for systems of equations, we're trying to find the coordinates of the point where it intersects. And that point is actually really clear for us to see that these intersect at 0, 6. Okay. And that's my final answer. That's the combination of x and y that make both equations true at the same time. Again, graphically, when we solve systems of equations, we're looking for the intersection point. And we clearly see that that intersection point is 0, 6. Okay. Now, you might be asking yourself, okay, why are there two other methods if we can just graph and find the intersection points? Well, sometimes the graphs aren't super easy to see what the intersection points are, okay? And sometimes we have some numbers that are difficult to graph or we don't have graph paper in front of us. So there's two other algebraic methods that we can use to solve systems of equations. The next one we're going to learn about is called substitution. Okay, it's called substitution. Now, the best way to think about the method of substitution is to think about what happens when your teacher is not in class, you have a substitute. So you're taking someone else and you're substituting your normal teacher for someone else. It's somebody that's filling in, okay? So what we're going to do here is we're going to get one of the variables, either x or y, in either one of the equations. We're going to isolate it, which means we get it all by itself. Okay, so we want to take the path of least resistance, okay? It is possible, if you look at this first 5x, it is very possible to rearrange this first equation and get this x right here all by itself. That is possible mathematically. Is that the path of least resistance? No, it's not. Okay, clearly the path of least resistance is to take the second equation and to get y all by itself. Now, y is already very close by itself. I just need to get rid of that negative coefficient. So I do that by dividing everything else by -1. And I end up getting y equals -2x plus 2. Y equals -2x plus 2. Okay, now the next thing that we do is once we isolate our variable, we're going to take this expression, okay, and we're going to substitute it in the other equation. Okay, so here's what we're going to do. We're going to take the other equation, which is 5x plus 6y, but instead of using y, we're going to substitute in what we already solved for y. We know that anywhere where I see a y, I can replace that with -2x plus 2, which is what I'm going to do. Okay, and that still equals -9. So again, all we did here with substitution is I took the first equation and I replaced the y that I saw with the y that I solved for with the second equation. So now you just have a pretty simple one variable equation to solve. So we have 5x minus 12x as I distribute the times 6 plus 12 equals -9. 5x minus 12x gives us -7x. Subtract 12 on both sides, and we get -21. Divide both sides by -7, and we get x equals 3. Now, what I see a lot of times is people do this awesome work with substitution, and they get the x value or y value, whatever they solve for first, and they stop. But remember, when we're solving systems of equations, we need to find an x value and a y value. We're looking for the intersection point. So now what you do is you take that equation that you already isolated for y, and you replace your x value in that equation. So that becomes -2 times 3 is -6 plus 2 gives me y equals -4. So the last thing that you have to do here is you have to you have to write those as an ordered pair, 3, -4. Because remember, the solution to a system of equations will be a coordinate of a point. So you have to write it as such, 3, -4. Okay, the next algebraic method that you're going to have to know how to use is called elimination. Okay, so this one says solve the system using elimination. Okay, so for elimination, our objective here is to get the coefficients of either x or y to be the same number or the opposite number. Okay, let me say that again. Our objective with elimination is we want the lead coefficients of either the x values or the y values to be the exact same number or opposites. Okay, so as I look at these coefficients, the first thing you always want to look at with elimination is make sure that everything is lined up accordingly. So make sure your x's are in one column, your y's are in a column, and then your equals and constants are all in one column. Okay, so then you want to decide, all right, I need to get one set of these coefficients to be the same. Okay, and what I'm going to do is I'm going to take the y coefficients, okay, and I'm going to get those to be the same. So if I've got a 3 and a 5, they would be the same if I can get them to be 15. Okay, so if you look at the first equation, okay, what should I multiply the first equation by to get the 3y to be 15? The answer is 5. So what you're going to do is you're actually going to rewrite this equation, and you're going to multiply everything by 5. So that becomes 25x minus 15y equals 210. 210. Okay, so then the next equation, ask yourself the same question. What do I need to multiply 5y by to get it to be 15? So I'm going to multiply by 3. Again, multiply everything by 3. So here I get 24x plus 15y equals 84. Okay? All right, so now what I've done is I've created a new system. So I have 25x minus 15y equals 210, and 24x plus 15y equals 84. So now what I'm going to do is I'm going to turn this into a big, giant addition or subtraction problem. Now here's how you decide whether you add these equations or subtract them. You look at the coefficients that are the same. If they're the same sign, both positive and both are both negative, you're going to subtract. If the signs are opposite from each other, you're going to add. Okay, so some of you need to go back and listen to that again. If the signs are the same, you subtract. If the signs are opposite, you add. So what that means is you go through each column and you add those values. So 25 plus 24 gives us 49x. Negative 15 plus positive 15 gives me 0y. And that's the goal. We want the variable that we're eliminating to be 0. That means it goes away. That's what elimination means. You're getting rid of a variable. Okay? So then 210 plus 84 is 294. So mission accomplished. We eliminated a variable. So now we have a really easy equation to solve. 49x equals 294. Divide both sides by 49 on a 4-function calculator, and you'll get that x equals 6. Now, again, don't stop there. You're not done yet. You also need to go back and find your y value. So pick either one of the equations. It doesn't matter which one. I'm just going to use the first equation because it comes first, okay? And we plug the x value in that we solved for. So replace the x with 6 and solve. 5 times 6 is 30. Minus 3y equals 42. Subtract 30 on both sides. We get negative 3y equals 12. Divide both sides by negative 3, and we get y equals negative 4. So there is my intersection point of those two lines, 6, negative 4. If I graphed those two lines, they would intersect at the point 6, negative 4. And what this represents is that's the only combination of x and y that makes both of these equations true at the same time. Okay? You're going to get a lot more practice with substitution and elimination in your homework, but this is just kind of a quick overview of how each method works. Okay? Now, the last thing that we're going to talk about in this lesson is two special cases. Okay? Special case number 1 is when you have no solution, and special case number 2 is when you have infinitely many solutions. Okay? So if you think about graphing again, what types of lines never intersect? It's okay to answer out loud, even if you're watching alone. Don't worry, no one will judge you. Okay, thank you. At least one person actually said the right answer out loud. It's parallel lines, okay? Parallel lines never intersect, therefore they can have no solution, okay? So infinitely many solutions is when you have two coinciding lines. Coinciding lines. In other words, when they're the same line, okay? When they're the same line. They lay right on top of each other. They're coinciding. That means they actually intersect at every single point. So that means there's infinitely many solutions. Well, there's a specific thing that you're going to look for to tell you the difference between parallel, no solution, and infinitely many solutions. Okay? So if you look at example 5, it says solve the system using any method. Okay? So very clearly, the best method here is going to be elimination. And I'm going to take the second equation and multiply it by 2. So when I multiply the second equation by 2, I get 4x plus 14y equals 20. Boy, and that looks familiar because it's the exact same thing as the first equation. So again, if I do elimination, I look to see the coefficients are the same sign, so I'm going to subtract each column. 4x minus 4x is 0x. Plus 0y equals 0. Well, that's convenient. We end up getting 0 equals 0. Whenever you get the conclusion that 0 equals 0, that is always true. 0 always equals 0. So that's the signal. That's the clue. That's how you know that you make the conclusion that this system has infinitely many solutions. Again, you know that you make the conclusion that it's infinitely many solutions if when you do elimination or substitution, you get everything to cancel out and you get 0 equals 0. That's the signal that it's infinitely many solutions. Now the next one, example 6, says solve the system using any method. Okay, you could do substitution or elimination on this one. I'm going to show you substitution. Okay, if we do substitution here, I'm going to solve for x on that first equation. So I get x equals, as I add x to one side, and then subtract 9 to the other. I get x equals 3y minus 9. And then I'm going to plug that in to my second equation. So negative 3 times 3y minus 9 plus 9y equals 12. I get negative 9y plus 27 plus 9y equals 12. Okay? Negative 9y and 9y are going to cancel each other out, so I end up getting 27 equals 12. Well, here's the problem. 27 never equals 12. That's not true. So when you get both variables to cancel out and you get a statement that's not 0 equals 0, you get some number that's not equal to the other side, okay? That's the signal, that's the clue, that's the dead giveaway that this system has no solution. In other words, these two lines are parallel. So that in a nutshell is solving systems of equations with two variables. Again, to summarize, you can graph the two equations and find the intersection point. You can use the method of substitution, where you solve for one variable and then plug that into the other equation. You could also use the method of elimination, where you eliminate one of the variables first and then solve. And then we have two special cases that we just talked about. When you get 0 equals 0, that means all the variables cancel out, and you're left with 0 equals 0. You make the conclusion that it's infinitely many solutions. And if you get both variables to cancel out and you don't get a true statement, you don't get 0 equals 0, you get a number that equals a different number, it's not true, you make the conclusion that you have no solution. All right, that's it for me. I'll see you next time. Good night.